Hello Nathan, I'm Federico, welcome to our institute. I'm a physicist and I work in the field of quantum cryptography, and today I would like to tell you a little bit of what we do in our job. So I would like to start by considering two people that we will call Alice and Bob, who want to exchange a secret message. And by secret message, I mean that we want that the content of this message is only accessible to Alice and Bob and to no one else, even if they get a copy of this message, okay? So this is how we mean it. So the way in which we want to achieve this goal, this task, is to give an encryption key to Alice and Bob. Both hold the same encryption key. So what is an encryption key? An encryption key is like a string of random numbers, okay? Like this. Okay. And we give both Alice and Bob the same string of random numbers. Then Alice, with this encryption key, will encrypt the message that she wants to send to Bob.
So then how does this encryption work? Is it just like taking the numbers and mixing them, or is it a special procedure? How should I imagine it?
There are different ways, but an easy way to imagine the encryption is the following. So the message she wants to send is going to be a string of letters, right? And some characters. So first you associate to every letter a number. And this is it's a predefined transformation, and it could be a very simple one, like every letter has a position in the alphabet, and you can associate the number corresponding to the position of the letter. So letter A is the first one, so the number for letter A is 1. Letter B is the second one, so the number for letter B is 2, like here. Okay? Yeah. After Alice converts her message in numbers in this way, she will then add, number by number, the random numbers of the encryption key to the numbers of the message. Okay? She will just do an addition. Okay? And in this way, she obtains a new string of numbers, okay, which are the addition of the numbers coming from the message and the random numbers of the encryption key. And this is now the encrypted message. She can now send it to Bob.
And then Bob would probably do the opposite to decrypt it by just subtracting the number.
Exactly, okay. You said it. Bob, to recover the message, will subtract the numbers of the encryption key and then do the opposite transformation of Alice to recover the letters of the message. Okay. Very well. Now, let's assume that in the middle, while there's a transmission from Alice to Bob and the encryption message, there is a malicious person that we will call Eve, who intercepts the encrypted message. So do you think that Eve is able to understand the content of the message?
No, I don't believe so, because Alice and Bob both hold the only way to encrypt and decrypt this message.
Exactly. So Eve doesn't know the encryption key, so for her, from her point of view, the message is just a string of random numbers. She doesn't understand anything. She doesn't know how to recover the letters of the message. Very well. So we now just talked about the whole deal, or a big deal, of cryptography, which is just to find a way for Alice and Bob to share, in the first place, this encryption key. Because once they have the encryption key, then we saw how the secret message can go, okay? And so this problem of sharing the encryption key without meeting each other, because otherwise it will be so annoying, no? That if I want to talk to you who live in another country, I have to meet you to give you my encryption key, right? So this problem is called private key distribution. And private because this key that they hold, the encryption key, needs to be private, so only known to Alice and Bob, the sender and the receiver. So there are two ways, or many ways, but let's say we're going to talk about two ways to distribute this private key. In traditional cryptography, Alice and Bob, since they don't meet, they're going to be connected by some communication channel. This can be a phone call, video call, email, but actually what they do is like some protocol on the internet, okay? This is their communication channel. Now, this communication channel can be wiretapped by our malicious party, or malicious person, Eve. So it means that Eve could listen to what they're saying in this channel, because in principle this channel is not protected. So this means that it's not safe for Alice and Bob to simply communicate the private key over the channel, right? Because Eve can listen to it, get the copy of the key. So how do they do that? How do they still establish a private key? They're going to use a very sophisticated algorithm to extract a private key, the same private key, for Alice and for Bob. And this algorithm is run over the communication channel. The security of the algorithm lies in the fact that there are some mathematical problems very hard to solve. So from the point of view of Eve, she would need to solve a very hard mathematical problem to also learn the private key.
So wouldn't that mean that by just solving this problem, the encryption is entirely defeated?
Yes, so in principle, if Eve is capable of solving this hard mathematical problem, she can get the private key. And if we said, as we said before, if she gets the private key, she can decrypt any message which is encrypted with that key, right? So it's completely unsafe then. And that's the point. This security guarantee of saying, it's a very hard mathematical problem, it's maybe not the best, because let's assume that Eve has a very powerful supercomputer that is built with future technology that Alice and Bob know anything about. Okay, so very powerful computer. So Alice and Bob are going to establish the private key in this way, but actually Eve has the computation capability to steal the private key. And so the communication that they will have in the future is unsafe. So in our work here at the Institute, we try to investigate safer ways for Alice and Bob to exchange a private key. And the protocols that we derive and discuss are called quantum key distribution, because we are distributing the private key, but we do it with quantum systems. And the great feature about this kind of cryptographic distribution of the key is that the security of these protocols is independent of the computational power of Eve. Okay, so even if she had that super powerful quantum computer with future technology, still she could not be able to obtain the private key with a quantum key distribution protocol. And let's say the main idea behind this security feature is that Alice and Bob are going to communicate with quantum systems. So whenever Eve tries to intercept these systems traveling, she's going to change the state of these systems, and therefore Alice and Bob can be aware of that. They will notice that something happened during the transmission. By exchanging quantum systems, Alice and Bob will realize if Eve is intercepting them, because she will change necessarily the state of these systems. So we can conclude saying that in principle, a private key established with quantum key distribution provides a higher level of security than a key established with traditional cryptography, the one we discussed before, because of simply the properties of quantum physics, and because we don't make any assumption on the computational power of an eavesdropper like Eve, right? Because in the cryptographic world, you want to be as safe as possible. So you don't want to make any assumption on the capabilities of your adversary. And that's why we work on these topics.
Okay, how can we verify that these qubits aren't manipulated in any way just by transferring them? Because when we do a copy of a file or just listen to what's transmitted, don't we already have a copy that can't be traced?
This is what I was saying before. So if Eve tries to intercept these quantum systems traveling between Alice and Bob, I said before that she necessarily modifies their state. Why? Because what she might attempt to do is to copy what is sent, right? As she would do with the normal communication, like with bits, right? You can always copy a bit. But the problem with quantum systems is that there's no way that you can copy the state of an unknown quantum system. So if you don't know the state of the system, you cannot copy it. And so any attempt at copying the state by Eve will necessarily modify the state of the system that is traveling between Alice and Bob. And that's why they're going to realize that something went wrong. How do they realize? Because in some rounds they're going to tell each other, look, I sent this, and Bob said, I received this. So if they compare these things, they're going to realize that sometimes there was somebody trying to change the state of these systems. Thank you for coming.
So our research is about quantum cryptography. Have you heard of quantum key distribution?
I have heard about cryptography and quantum mechanics, but not this specific link between those two.
Okay. So quantum key distribution, the idea of key distribution is that we have Alice, which are going to be always our characters. So Alice and Bob, they want to communicate secretly, and for that they need to establish a secret key. Okay? And the idea of quantum key distribution is to use quantum mechanics, so quantum systems, and make measurements on these systems in order to generate this key. So basically the key will be constituted by the measurement outcomes of some quantum experiment. Okay? But actually, I want to talk to you about something a little bit more advanced, because actually quantum mechanics allow us to have security in an even more adversarial scenario. Because so far I told you that Alice and Bob, they share quantum systems, and they are going to make measurements on these systems. But maybe they don't have a way to very well characterize these systems, or maybe it could be even the case that the eavesdropper is preparing the systems that they are going to measure. So how can they be sure that they actually have the quantum system that they expect to have? So this more adversarial scenario is called device-independent scenario, where we don't want to rely on the description of the measurement that we are performing or of the systems that Alice and Bob are measuring, okay? So in this very adversarial scenario, the security will rely only on the statistics of the outcomes that they observe. Okay. So without saying what this outcome refers to which specific measurement. So maybe in order to explain the device-independent scenario a bit better, let's take a step back and talk a little bit about correlations. Okay, and for that, let's see an example to understand about correlations. Okay. So I have prepared two boxes, box 1 and box 2, and then inside these boxes there is a ball, and this ball is either blue or red, and it's either made of plastic or made of wood. Okay, so well, we will do it a couple of times. You check what is inside each box, and then you let me know, and then we are going to make a table here. Okay. So you can open the box and make an experiment.
And I just tell you exactly
the color and the material of the...
Okay, so we have a red ball, which is made of plastic.
Okay, so red ball and it's of plastic.
And box 2?
Yeah.
It's a blue ball and it's made of plastic.
Okay. So now I'm going to prepare again. Good, so let's repeat the experiment.
So in box 1 we have a red ball which is made of wood.
Okay.
And in box 2 we have a blue ball which is made of wood.
Okay. Right, so let's suppose that we repeated it several times, and we repeat a third round, but then actually we had this. And so on. Okay, so here we have just a few instances of our experiment, but suppose we have done it several times. And what can you observe about these properties of the balls that were inside the box?
Well, first for the material, it's perfectly, I call it correlated, because we always have either both plastic balls or both wooden balls.
Yeah.
And for the colors, we always have a mixture. There's one red and one blue ball.
So they are always the opposite colors, right? Yes. And I mean, also it seems a bit like they are random. Like either I have with the same probability plastic, or I have the same with the same probability wood. So if we would have done it really several times, we could talk about probabilities. But let's say that then the probabilities that we have red for the first box and blue for the second box was half. And the probability that we have blue for the first and red for the second was also 1/2. And regarding the materials, we have actually that plastic for box 1 and plastic for box 2 has probability 1/2, and wood for box 1 and wood for box 2 has probability 1/2. Okay, so I mean, with that you can conclude, oh, the properties, they seem random, so either I have plastic or wood, I don't know what is going to happen, but every time I have plastic in one box, I have it on the other box, so we observe correlation, and we will observe some randomness, okay? So, but now, so it can be that these boxes are very correlated, but now I tell you how I actually have prepared the boxes, and I actually have written it here, the secret of how I have prepared these boxes. So first of all, I toss the coin, so my first coin, and then if I had head, I would put a red ball in the box 1 and a blue ball, an opposite color, in the box 2. If I have tails, I put a blue ball in box 1 and then a red ball in box 2. And then I toss a second coin to decide in what's going to be the material of this box. Okay, so if it was head, I would put both plastic balls, and if it was tails, I would put both wooden balls. Okay. So even though you observe the correlations and randomness, actually if you would know the values of my coins, you would know exactly what was the color and the material for each of these instances, okay? So this is the idea of the case where, okay, I observe correlation, I have some randomness, but there is a hidden variable, which here was my coins, or there is like a causal explanation for these correlations that I'm observing. Okay, so now let's go back to our device-independent scenario. So as I said before, I want to model the experiment of Alice and Bob without talking about the details of the experiments. So this is, we say that we are modeling it as boxes, as black boxes. I don't know what is inside, so this is Alice's experiment, and this is Bob's experiment. And Bob can measure, and Alice and Bob, they can measure two different properties of our system. Like in similar way, you measure the color or you measure the material, but they are going to measure some quantum properties. So this is some button in these boxes that Alice can press, and it's going to determine what is the measurement, what is the experiment that Alice is doing. And the same way, Bob has two measurements that he can do. Okay, I will call here X, for example. Can be 1 or 2, so meaning Alice makes this experiment or she makes this experiment. And then this box is going to have some outcomes. So for example, oh, this was the outcome that clicked. So I will call this outcome A. And the same way, Bob can have two outcomes, and this outcome is B. Okay? So after they do the experiment several times, they do a similar table to the one that we have done for the two boxes, where they are measuring what are the probabilities that Alice gets outcome A and Bob gets outcome B. When Alice chose to perform one experiment that here we are labeling X, I'm not saying which experiment it is, it's just the label that matters, and the experiment Y.
So why is an experiment from Bob?
Yes, exactly.
Okay.
So, so therefore, in the device-independent scenario, I get rid of the description of my system and I talk only about the probability distributions, okay? And now we are interested to see, okay, can I guarantee that these probability distributions, these correlations, they are really random, and they are strong, but they are really random, or there is an explanation for these correlations, okay? And for that, we have the concept of a Bell inequality. I don't know if you heard about that before.
Yes, but I'm not quite experienced with them.
Okay. But a Bell inequality is basically a function of these probability distributions, okay? And so this function will have a bound. And this bound, we are going to look, okay, if my probability distribution has an explanation for these correlations that I'm observing and this randomness that is from another variable from the past or has a hidden variable that can explain this correlation, then this probability distribution can only achieve a certain bound for this function, okay? But then the point is quantum mechanics violates such Bell inequality. And by violating a Bell inequality, then we can be sure there exists no hidden variable that could explain or that could determine perfectly what are the outcomes of of these measurements that Alice and Bob are doing.
Okay, so by performing an experiment and violating the Bell inequality, we can therefore conclude that there are no local hidden variables which can explain this outcome.
Exactly.
Okay.
And if there is no such hidden variables, Eve, which is the eavesdropper, the malicious part, cannot have access to such variable as well because it doesn't exist. Yeah. So that is the intuitive idea to ensure the security of device-independent quantum key distribution.
So it's actually a very geometrical topic.
It's a very geometrical topic indeed.
Okay. Yeah. Sounds very interesting.
So, Felix, probably you heard that with a device-independent quantum key distribution protocol, two parties, Alice and Bob, can establish a private key, and the security of this key is independent of the actual devices they use to implement the protocol, and instead is only based on the observation of no-local correlations in their outcomes, which is certified by the violation of a Bell inequality. The length of the final key that the parties are going to obtain depends on two quantities, and the first quantity is the entropy of the outcomes of Eve with respect to Bob. And this quantity quantifies how much Eve is uncertain about the outcomes of Alice and therefore about the key bits. So the higher the entropy, the longer the key. The other quantity instead is related to how much the outcomes of Alice and Bob are correlated, because in the end they have to share the same key, so they need to be equal. Now, an important point to stress is that in order for Alice and Bob to observe non-local correlations, the state of their quantum systems must be entangled. Have you ever heard about entanglement?
Oh yeah, I had a course where I heard about this. Okay. So entanglement for me seems somehow that I have two atoms, for example, and they share somehow the same state or superposition. But a priori, before I do a measurement, I do not know which outcome I will have. But one, as far as I know one, I also know the other.
Exactly, it's exactly this. You said it. As soon as you observe and measure one or two systems, also the state of the other system is completely determined. And entanglement allows Alice and Bob to obtain the correlations they need to violate the Bell inequality, so no local correlations, and also allows the outcomes of Alice and Bob to be equal and form a shared private key. Okay, now the interesting thing is that theory allows and experiment confirms that we can have more than two parties sharing an entangled state. So this means that we can have four parties like Alice, Bob, Charlie, David, each holding a quantum system. These systems can be all entangled with each other. What happens in this case? The parties can decide to test a multi-parted Bell inequality, and if they violate it, they can extract from this a conference key. Now, this key is called conference key because it's going to be the same key for each of the parties. And the protocol that does so is called device-independent conference key agreement. So it's a generalization of device-independent quantum key distribution. It just has a different name. What is a conference key for? Well, for instance, if you have a group of parties who want to share a secret, they're going to encrypt it and decrypt it with the same conference key. So
and everybody needs the same key.
Exactly, everybody. That's why it's called conference key.
Yeah.
Okay. You know, conferences, online conferences is a very important topic nowadays. Good. Now, there's an important remark to make, however, which is about correlations. So the correlations that these parties observe when they violate a Bell inequality, a multi-party Bell inequality, do not necessarily imply that their outcomes are all equal to each other. So this means that we can have different types of correlations when we have more parties. For instance, we can have the correlation where all the outcomes are equal. So let's assume we have just three parties for simplicity. We have Alice, Bob, and Charlie. Okay, and equal outcomes means that they are either going to obtain the result +1 or the result -1. these kind of outcomes are the ones they would use also to extract a conference key, because they have the same outcome.
So in that case, everybody would have the same key, because everybody has the same outcome of the experiment.
Perfect, yes. But another type of correlation that exists is when, for instance, the product of the outcomes is +1. In this case, the outcomes of Alice, Bob, and Charlie can be, for instance, 1, -1, -1, -1, 1, -1, or -1, -1, 1, or also 1, 1, 1. Yeah, these are all the cases. Now, you see that for these type of correlations, although they're very strong because they always guarantee somehow that the product of their outcomes is +1, at the same time, though, there's always going to be a party with a different outcome.
So overall, they are correlated, but the outcomes themselves, they may differ or be distinct.
Exactly, perfect. And so this is not ideal if one wants to extract a conference key which is shared by everybody, right? And in fact, there exist Bell inequalities violated by local correlations, which are strong, but the outcomes of the parties are not all the same. Mm-hmm. And so these Bell inequalities cannot be used for the task of device-independent conference key agreement, what we said before.
But what should it be used then for?
They can be used for a similar task, a simpler one, which can be called device-independent randomness expansion. Okay, so in this case, the goal is simply to prove that the outcome of a party or a set of parties are intrinsically random from the point of view of the eavesdropper Eve. So they're secret, okay? But we don't care anymore whether the outcomes of all the parties are equal or not. So we don't need a private key in the end, but we want just to have that the outcomes are secret. And what is that for? Well, what they obtain in the end is secret randomness, right? Secret outcomes. And this is actually a very important primitive of cryptography. Many protocols require at some point the use of secret randomness. So a string of random bits that you're sure nobody else knows. And device-independent randomness expansion allows you to obtain so in a device-independent way. So without trusting the devices that produce these bits.
So I would somehow have a network of devices that somehow communicate with each other and generate me random outputs that I could use for my algorithms or for establishing keys.
Exactly. And you're sure that only you and eventually the other parties that contributed in testing the inequality might know the outcomes. You, of course, know them. They are yours. But any external party doesn't know them.
And if I have a big group of participants, it is very unlikely to know what the others had in their experiment.
But still, the theory allows you to prove with certainty that anybody who does not participate in the experiment, so let's say an external party, Eve, malicious party, Eve will never know what are the outcomes that you obtained.
All right.
Okay? Yeah, so maybe now I can show you some of the results that we obtained in our work related to these topics. Right?
That would be great.
Okay. In these plots, we plotted the entropy of the outcomes of, for instance, Alice and Bob, when we have Alice, Bob, and Charlie testing the inequality, or just the outcome of Alice on the right-hand side, with respect to Eve, okay? So the higher the entropy on the right side of these plots, the more Eve is uncertain about these outcomes. And of course, the higher the violation, the higher will be the entropy. Now, what's interesting is that in our first work, because of the Bell inequality that we chose to study, the local correlations that violated this Bell inequality are such that the outcomes of the parties are never all the same. And so such a Bell inequality, as I was explaining before, cannot be used for device-independent conference key agreement. However, it can still be useful for device-independent randomness expansion. And in fact, as you see, the black line here is the entropy for the Bell inequality that we first studied. And you see that it guarantees the highest amount of entropy among, let's say, the other cases that we studied, right? However, so this tells us that we can definitely use this inequality for device-independent randomness expansion, but not for conference key agreement. And in a second work, which is instead almost completed, we studied a different Bell inequality. And in this case, the correlations of the parties guarantee that the outcomes are also all equal to each other, and therefore the parties can obtain a conference key in a device-independent way.
So you found an inequality that maximizes over all other inequalities that are known before, the entropy.
I wouldn't be so optimistic in the sense that it's certainly the best entropy that we have among the ones that we studied, and among maybe the most common ones. But I wouldn't sign something saying that it's the best ever. Okay, so it's a good result.
But it comes at the cost that you cannot use that for private key.
Exactly, it's an inequality that is very good for instance, having randomness of two parties, but it's unusable to extract a key. And in the second work, instead, we extract a key, but the green line is the second work. We have much less entropy for two parties, but we can extract a key.
Cool.
Okay, so thank you for coming, and I hope that this clarified a bit what we do here.
Thank you very much.
You're welcome.
Yeah, so I remember that when I came to Düsseldorf, I was already interested in this problem of bounding the von Neumann entropy for any other inequality beyond this, the simple CHS-H scenario. And because I think this is also a very interesting problem from the fundamental point of view, because it's very difficult by the fact that we are in this very adversarial scenario where there is no assumption. But also it has applications, because if we would get some better bounds, it can lead to better protocols that are more robust and so on. Yeah, so I remember our first discussions when I came here, also together with Herman. So you were also interested in this problem. And then we were wondering, okay, so which scenario we are going to attack first? Yeah, so then after some time, we decided to go to consider this multipartite scenario, and first with this Bell inequality where we had some symmetries that would simplify the problem. So yeah, in my mind, that was how the project started.
Yeah, that's true. Actually, it came really naturally, right? Because we in Düsseldorf, we designed and analyzed the first device-dependent multipartite QKD protocols. And then while you were still in Delft, you were designing the first device-independent protocols for many parties. And then you joined the group here. And yeah, then we could merge the expertise of both groups together. And it was really a good start to the project. And it also, it fits very well into the cluster. So it is a fundamental theoretical project that is maybe aimed at the end of the cluster to be implemented in an experiment. So we have this experimental group in Bonn of Martin Weitz, who expects to produce photonic multipartite entangled states. And within the timeline of the cluster, we would be really happy if we reach our challenging goal to implement these protocols. So that's somehow the aim within the cluster. And it fits also into the general goal to have matter and light interacting for quantum computation and quantum communication. So matter qubits and light qubits have to come together, they have to be linked. And then once this is managed by the experimentalists, they can produce multipartite entangled states, and we can actually find out what these states are good for, how they can be applied in protocols, and maybe in the far future, as a far future vision, how these states can be used in the quantum internet.
Mm-hmm. Yeah, maybe that's also another point that we, let's say, we aim to investigate in our research would be this trade-off between implementing these protocols using only bipartite links. And I feel that what we are more interested here is, okay, let's look at multipartite entangled, which is like something that exists in quantum mechanics, and see how it can outperform or not outperform the equivalent protocols that are only based on bipartite links.
Mm-hmm. Yeah, that's true. And actually, I think we know very little about this. So we know that most protocols can be done with bipartite entanglement. We also know that some multipartite entangled states can be used for QKD. But for most of the states, we don't know anything. So we still have a lot to do to get a more complete picture of the whole situation.
Indeed.
Indeed.